Hi class, this is Adam Ward, and I want to talk with you today about material from Chopra Lectures 1 and 2. Specifically today we're going to talk about rates, unit conversions, and stoichiometry. These are fundamental concepts that are outlined in the textbook and that you should be comfortable with for the remainder of the semester. So I want to start with fundamental units. We can think of our units as in the MLT or FLT systems. That's mass length time or force length time. So mass with an M, if we think about the BG or British gravitational system, mass is in slugs. Common mistake, people think mass is going to be in pounds, but it's in slugs in fact. And in the SI system, commonly the metric system, mass is fundamentally grams, kilograms, milligrams. Length, similarly, feet or meters. Time, we'll use a capital T, seconds in both systems. And force, pounds and newtons. And so one of the biggest problems I think people come across is what is the difference between a mass and a force? But of course, you've all seen this already in your lifetimes, whether you know it or not. And you've seen it through Newton's second law, F equals ma. Now, what that means is force equals mass times acceleration. In the case of weight on Earth, we'd measure that as a force, and we measure it in pounds. That's the effect of gravitational acceleration acting on a mass. So pounds are actually slugs times feet per second squared, and newtons are kilograms times meters per second squared. Do you need to memorize all of this? Absolutely not. Do you need to know the difference between force and mass? Yes, you do. And you can use F equals ma to make that. One of the units that you may be less familiar with is concentration, the mass of a constituent per unit volume of a solution. Typical dimensions here are mass per volume or a mass per length scale cubed. Units like milligrams per liter, kilograms per cubic meter. One thing to be careful of here, we'll use in this class L for liters, which is a volume or a length scale cubed. And so that's something that you want to be careful with, knowing if you're talking about liters or length scales throughout the semester. Almost universally we'll be talking about liters when we use a capital L, but it's something to keep in mind. One other way that we try to express concentration in this course is what's known as the parts per system. And the idea is the same. It's the mass of constituent per mass of solution. But we take our solution and treat it as though it's pure water, which has a density of 1 gram per cubic centimeter. So I want to show you how this parts per system might work. So let's take an example. We have 1 gram of X, whatever X might be, in 1 cubic meter of water. Now we can do a unit conversion here and use the density. So 1 cubic meter of water weighs 1,000 kilograms, and 1 kilogram is equivalent to 1,000 grams. If you cancel your units, you end up with 1 gram of X per 1 million grams of water. So 1 gram of X in 1 million, or 10 to the 6th grams of water, or 1 part X per million parts water. So when we use the parts per system, we're still expressing concentration, we're just doing it in a way that's a bit shorthand. How does this play out in terms of useful units? This parts per million system can be extended into parts per thousand, parts per million, per billion, or per trillion. And depending on what constituent we're working with, we might use any of these. So if we're working on total dissolved solids or salinity, things that are relatively large values, we might be looking at parts per thousand. So 1 in 1,000, for example. We'll work a lot in this class with dissolved oxygen, biological oxygen demand, nitrogen concentrations, commonly parts per million or ppm. Now one important thing to note here is ppm can be directly converted into grams per cubic meter or milligrams per liter. You can also prove to yourself that milligrams per liter and grams per cubic meter are equivalent measurements. So you can go through a dimensional analysis and do those conversions, or you can shorthand know that milligrams per liter and grams per cubic meter and ppm could all be converted from one to the other. Most common in this class will be, as I said, the parts per million. So an opportunity to test yourself if you're not comfortable here. Can you convert 12 milligrams per liter to kilograms per meter cubed and to parts per trillion? If that's an exercise that you want to take on, go ahead and work through it, and you can email me and get the answer. In addition to concentration, we'll have to get a little comfortable with rates in this class and some basic conversions between fluxes, flow rates, and mass loading rates. And so I want to take a moment to show you through this. This very tightly parallels some of Chopra's presentation in Lecture 2 in your textbook. In this class, for flow rate, or what's commonly thought of as discharge, volumetric flow, so the amount of water per time, or a volume per time moving through a system, we'll use a capital Q in this class. Notice the basic units are length cubed per time, and you can calculate that as the cross-sectional area times an average velocity. Typical units might be cubic feet per second, liters per second, or meters cubed per second. Mass loading rate in this class, we'll use a capital W. We're talking about mass per time, and you can calculate that as a discharge, Q, times a concentration. Typical units might be kilograms per day, pounds per week, anything where we're looking at, slugs per week, anything that we're looking at a mass per unit time. And finally, flux. Flux is a W per unit area. And so in this class, we'll use a capital J to represent fluxes. And I'm showing you the basic unit calculation there. So a mass per time, that's a W, multiplied by 1 over length squared, so divided by area. So a flux is a mass per time per area. So who cares? Well, maybe the deposition from the atmosphere into our lake is 10 kilograms per day per square meter. Well, the total amount getting in the lake then depends on how big the lake is. So there's an instance where you might want to use a flux instead of a mass loading rate. And you can calculate that as the velocity across that area times the concentration. One thing that we'll want you to be comfortable with in this class is converting between flow rates, mass loading rates, and fluxes, and knowing the difference between those. If you're unsure, a good thing to do is check your units. If you're not sure if you're given a flux or a mass loading rate or a flow rate, check the units, because they're all different. So in this course, starting with the units may be a way to help you identify what you've got. Before I start on this, I'm going to pause Docere and start this as a new topic, so folks who want to just see the examples can do that. Stay tuned.